So this brings us to section 11.2, the rate law. So we have a way to express this relationship between rate and concentration, and we're going to call it reaction order, and we're going to talk about that in a little bit. So for a general reaction, or a general equation, AA plus BB goes to CC and DD, we can determine a rate law that is going to be relative to the concentrations of A and B, some exponential factor, we're going to call this the reaction order, and this value K, it's a proportionality constant, sometimes called the rate constant. And this is going to be constant as long as the temperature remains constant. So at a given temperature, so K at 25C, for example, is going to be a constant. If you change the temperature, what we're going to see is that as our temperature goes up, K is going to go up too. But N and M are what's called the order of the reaction with respect to each reactant. And the value of N and M have to be determined by experiment. You can't just look at the balanced chemical equations. So these are not stoichiometric coefficients. They're not the stoichiometric coefficients from the balanced chemical equation. So the rate constant K is specific for a given reaction at a given temperature. The reaction order defines how the rate is affected by the reaction concentration. For example, if rate doubles when the concentration of A doubles, then the reaction order is 1. If the rate quadruples when the concentration of A doubles, then the reaction order is going to be 2. Right? So what it's saying is for a first order, this guy's called first order, my concentration affects my rate of reaction. Right? And for a second order, my concentration strongly affects my rate of reaction. So let's look at some values for this rate constant K. It's going to depend on how that rate is defined. So in our NO2 example, we've got our 2 NO2s giving us to 2 NOs and some oxygen gas. So our rate is going to be defined in terms of the consumption of NO2. So we're going to say minus change in NO2 per rate of time is equal to K times NO to the N. And we don't know what N is yet. Or we could define rate in terms of production of O2. So we're going to say rate prime, and this little symbol here means prime. And that prime just means we're looking at it from a different perspective than we're used to. So we could say our rate prime is going to be from the oxygen's perspective, and we could say, well, it's going to be some value K prime times NO2's concentration to the N order. Since 2 NO2 molecules are consumed for every O2, our rate is going to be twice the prime rate. So K for the NO2 raised to the N is going to be equal to 2K prime for the NO2 raised to the N. So our K is going to be twice K prime. So there is a stoichiometry relationship between our K and our K prime. Honestly, we're not going to do too much with these primes. I just need to tell you that they're out there because sometimes you will see them. Right. We've got different types of rate laws. So we have what's called a differential rate law. That's expressing how the rates depend on the concentration. And then we've got what's called the integrated rate law, and that's expressing how the concentrations are going to depend on time. So upon determining the differential rate law for a given reaction, the form of the integrated rate law for the reaction is automatically known. So there is a tie-in between the differential and the integrated forms of the rate law, but we can't just say, oh, based on the balanced chemical equation. Right? We need to do that experiment to find out what our reaction order is. So let's sum up. We typically consider reactions only under conditions where the reverse reaction is unimportant. So we're always looking at something that's going forward. Our rate laws will involve only concentrations of reactants. So we're going to try to view things from the reactant's point of view. Because the differential and integrated rate laws for a given reaction are related in a well-defined way, the experimental determination of either way is sufficient. So if you can figure out what the integrated rate law is, or you can figure out what the differential rate law is, it's not going to matter which one you figure out because they're related to each other pretty easily. And experimental convenience is going to tell us which way we're going to do that. And usually what we're going to see is that there's two ways to do it. One's called the method of initial rates, and the other is going to take a whole bunch of data and analyze the shape of the curve to figure out what the reaction order is. In PChem lab, we will do both of those if you stay along in the chemistry journey with me. But knowing the rate law for a reaction is important mainly because we can usually infer the individual steps. So from our rate laws, we can often figure out stuff about the mechanism that that particular reaction undergoes. So section 11.3, determining the form of the rate law. So we said that there is this rate expression. So rate is going to be K times the concentration of our reactant raised to some power, might involve another reactant raised to another power, N and M, right? It's going to involve experimentally calculating the power to which each reactant concentration must be raised in the rate law. For a first order reaction, right, N is going to be equal to 1, and M, or all the other ones, are going to be equal to 0, right? Anything else has to be 0. So it's just looking at one thing, and this guy's going to be raised to the first power. Doubling the concentration of A makes our reaction happen twice as fast. And if you stop and you think about this, like, okay, if I throw gasoline onto a fire, if I double the amount of gasoline, I'm going to get twice the amount of fire out, right? So that would be a first order type of reaction. The first thing we'll look at is what's called the method of initial rates. It's a common method for experimentally determining the form of a rate of reaction. You're going to set up a series of experiments and look at the rates of reaction. So the instantaneous rate determined just after the reaction begins. So we'll say, well, here's our T0. And the value is going to determine for the experiment the same value of T or as close to possible as T0. The idea is to determine the instantaneous rate before the concentrations change. Right? So this is why you want it to be instant, because if our reaction rate depends on concentration, over time, what's happening to our concentration? It is changing. So we need to have some sort of snapshot where we're not looking at what is a change in temperature or change in time, right? We need that instantaneous tangential point. Because if I take my average out here, well, my average for that longer time period is going to be at a different slope and a different rate. So we need that instantaneous one. Ideally, what is my tangent line right up here at the beginning? Right? So several experiments are typically carried out using different initial concentrations. So what you're going to do is you're going to change the concentration of each of the reactants and then measure the rate. The initial rate is then determined for each run. Results are compared between runs to see how the initial rate depends on the initial concentrations. So our overall reaction order is going to be the sum of the orders for the various reactants. So if we do an experiment where we've got two different reactants, A and B, they could very well have two different reaction orders, N and M, and our overall reaction is just going to be N plus N, N plus M. So if this guy is first order and this guy is second, our overall is going to be 1 plus 2. It's going to be an overall third order reaction. K is still our rate constant. What we'll see is that the units on that are going to change, but A is concentration of A in square brackets is the concentration of reactant A, and the square brackets around B tell me it's the concentration of reactants B in moles per liter. All right, so let's do a quick concept check. All right, so how do the exponents or orders in rate laws compare to the coefficients of the balanced chemical equations, and why? All right, pause, think about it. Hopefully it should be you said that there is no relationship between those balanced chemical equations and the exponents or orders in those rate laws. You could have something that is 4A plus 2B goes to C and D, and that C and D, right, not going to show up. the order for A might be 1 and the order for B might be 3, even though they're going to have different stoichiometric coefficients in the balanced chemical equations. That's not necessarily relevant to the reaction orders. Right? Those are things that have to be experimentally determined. Section 11.3, determining the form of the rate law. So if we've got different reaction rates, the three most important ones are going to be 0th order, 1st order, and 2nd order. And what I've got here is a plot of reactant concentration versus time. This is our raw data. Right? So as we change, what we're going to see is that for a 0th order, it's a straight line. Right? Nice straight line. For a 1st order reaction, it's going to change over time, and it's going to slow down as we start to use up reactants, because if our rate is going to be some fudge factor K times the concentration of A to the 1st power, as we lose A, our rate's going to be smaller, right? So if A goes down, my rate goes down. Right? If it's 2nd order, so our rate is going to be equal to K times the concentration of A squared, right? It's going to slow down even faster. So it's going to go flatter quicker. So it's got an even stronger dependence on the concentration of A. And just kind of looking at it, right, you can tell which one is the straight line, the 0th order one. But what if you see a curvy line? How do I know if it's 1st order or 2nd order? Right? I'm going to need another way to linearize my data, just like we saw with Clausius-Clapeyron. Is there going to be a way to give us nice linear data out of our 1st and 2nd order? And TLDR, there is. Right? So if you look at the rate and how the rate is changing, so this is rate on here as a function of A. If it's 0th order, it has no dependence on the concentration of A. Is concentration go up or down, your rate's not going to change. If you're 1st order, it's a nice linear relationship for rate with A. And if it's 2nd order, your rate is going to exponentially change. It can be an e to the something type of rule. Right, so let's look at these. So we've got a reaction between bromate ions and bromide ions in acidic solution is going to give us the following reaction. We're going to take some bromate and some bromide, and we're going to react it with H plus to give us Br2 liquid, which is orange, and H2O liquid, which is clear. So we're going to take some clear stuff and we're going to generate that orange color. So if we look at a table for the following results, we're going to run 1, 2, 3, 4 experiments. 1, 2, 3, 4. And if we look at our initial concentrations here between run 1 and run 2, what did we do to the concentration of the bromate? It doubled, right? And here, for the bromide, it's going to stay the same. If I look at the rate, concentration of H plus stayed the same. So if I look at the rate over here, what happened to the rate? Right, it got faster. How much faster did it get is the question we're going to ask. And then if we look at experiments 2 and 3, right, between here, this stayed the same, and this doubled. And what happened to the rate between here and here? Right? So between our 1st and our 2nd experiment, our rate doubled. So we know that this guy is going to be 1st order with respect to the bromate. It's going to be rate, it's going to be K times the bromate. And we said that this guy's going to be 1st order. And if we look at the Br minus the bromide going between here and here, this guy also doubled. So this guy is going to be 1st order with respect to bromide. So our overall order is going to be 2nd, but it's going to be 1st order with respect to each of those reactants. If we look at the concentration of H plus in experiments 3 and 4, right? And we look over here between 3 and 4, there was no change, right? So for H plus, it's 0th order. So let's take a look. So we're going to look at those reactants. We're going to look at the overall reaction order, and we're going to figure out the value for that rate constant, because you're going to want to do that. Like, what's the numerical value I can put on K, right? What number does K have? Okay. So the general form of our rate law for this reaction is going to be K times the bromate to the N times the bromide to the M times the H plus concentration to the P. We're going to determine the value of N by looking at the results from experiments 1 and 2. So only the bromide concentration changes. So you're going to take your rate for 2 divided by the rate of 1. That was 1.6 times 10 to the third divided by 1.8 times 10 to the fourth. And then we're going to multiply it by K times 0.2 moles per liter times 0.1 mole per liter times 0.1 mole per liter to the P. And what we're going to see is, like, a lot of these are going to cancel out. What happens to my Ks? They canceled out. What happens to this 0.1 moles per liter to the M? That cancels out. And this cancels out. So the only thing that's changing is this. So if we look at these ratios of the rates, the rate ratio, and we look at the ratio of the two reaction concentrations, we end up with 2 to the N. So N is going to be equal to 1. We're going to do the same thing. We're going to look at rate 3 over rate 2. Right, so these guys are our two relative rates, and that comes out as 2. Again, we're going to say it's equal to K times the other part. So this would be the bromate to the 1. We know it's to the 1 now, but those are going to drop out. These guys are going to drop out, leaving us this ratio of concentrations. That goes in here. So our rate doubled when our concentration doubled. All right. Our concentration doubled. So we're going to end up with M also being to the first power. So to determine the value of P, we're going to look at the results from experiments 1 and 4. So we're going to take our ratio of our rates from 1 and 4. We'll get 4x. Oh, I told you wrong in the beginning. So this is going to cancel out. These guys will cancel out. And here we're doubling the concentration of H+. So in here we've got 4 is equal to 2 to the P. P has got to be equal to 2. So the rate of this reaction is first order with bromate and bromide, and second order with respect to H+. Therefore, our overall reaction order is going to be N plus M plus P, or 4. So we're going to write this out as our rate is equal to K times BrO3 to the first power times Br minus to the first power times H plus concentration to the second power. And all you do to solve for K is you go back to any one of those initial experiments and plug in the values for the 3 different concentrations and put in the one value for the rate that you calculated and just solve for K. Right? So for experiment number 1, the initial rate was 8 times 10 to the 4 moles per liter per second. We had a concentration of bromide and bromate and a concentration of H+. Why pick this? Because the math is easy, right? So this guy is going to be 8 times 10 to the 4 moles per liter per second is equal to K, which we're solving for, times 0.1 to the first power, times 0.1 to the first power, times 0.1 to the second power. So this guy's a 2. So we're going to get 8 times 10 to the minus 4 moles per liter per second is equal to K times 1 times 10 to the minus 4 moles to the 4th liters to the 4th. So K is going to be, solve for this, we're going to rearrange it, and notice what our units come out to. Right? Our units on K are going to end up as liters cubed per moles cubed per second. So this is going to end up as molar to the minus 3 seconds to the minus 1. And anytime you have a 4th order reactant, the units are always going to be m to the minus 3 seconds to the minus 1. Okay? And that's a trend that's going to show up for all of these Ks. So looking at your overall reaction order, if you're 0th, your rate law is going to be rate is equal to K. And the units are going to be molar per second or molar times seconds to the minus 1. If you are first order, your rate will be K times A to the first power, and your units are going to be seconds to the minus 1 or per second. If you are second order, your rate's going to be K times A to the first times B to the fourth, or it could be A squared, right? Either one is going to give you the same thing. And that's going to give you units of 1 over molar per second, or molar to the minus 1 second to the minus 1. If you have third order, it's going to be A, K times A to the first and B to the second, or it could be A to the second and B to the 1, or it could be A to the 1, B to the 1, and C to the 1. As long as it is third order, your units are going to end up as molar to the minus 2 seconds to the minus 1. So what's consistent? They're all going to have seconds to the minus 1. And then it's going to be molar to the minus whatever the reaction order is, minus 1. Okay. It's just a little trend there. So for the reaction where A plus B goes to C and D, the experimental rate law is rate is equal to K times A squared times B. What is the order with respect to A and B, respectively? Pause. Tell me your answer. All right, well, up here we've got this as second order with respect to A. So we're going to look for this. These are my two that have second order. We'll get rid of these guys. It is first order with respect to B, so D is gone. It leaves us with C. All right, another quick question. So for that same reaction where we've got second order with respect to A and first order with respect to B, what is our overall order for the reaction? It's just going to be 2 plus 1 is third. What are the units on K? Are going to be molar to the minus 2 times seconds to the minus 1. And the reason is that your rate, this dude over here, is always going to be in molar per second. So in order for all of these exponents and concentrations to work out so that this rate number here is in molar per second, the units on K have to work out to make it equal to molar per second, because you're multiplying by per molar twice, per molar, right?